So, we will come to now the open die forging analysis. So, what are the things which people consider when you discuss with when you deal with the open die forging? The simple example of an open die forging is the cogging. So, and as we have mentioned earlier, the large billets, they have to break down the structure, because large billets will always contain large amount of interdendritic segregation, coring, maybe some internal defects, gas porosities, all those things may be there, and its size is also relatively very large. So, normally by open die forging, people just reduce the cross sectional area, and in general the cross sectional area will be maintained the same similar, but it is not that always it will be like that, but in general if it is a square cross sectional area, people will prefer to have a square cross sectional area. So, they will keep on rotating after each forging operation, after each impact, or and these are generally done by power press or pneumatic press or even hydraulic press also, they can do it. And this figure also tells that it is kept on a bottom punch, bottom die, and the billet is kept in between, then from the top it is just impacting at this region, this shaded region it is there. So, with the width B, and the width of the billet is W0, and then it is just compressed by applying a compressive force, it is being compressed. Normally the hydraulic press or power hammers are generally used for this purpose, because you need a very high capacity press for this, because the billets are very large in number. So, when you are doing this, the billet size is much larger than your tools. At any time when you look at it, the deformation is confined to a small area like this, it is only confined to this small area, not along the full length of the your ingot. So, that is one thing. So, at every stage a deformation, it just deforms by a small amount, not small amount, it just deforms. There is a change in the cross section area, you may rotate it by 90 degree. So, that now again, so the moment it is pressing, normally the lateral flow of the material will be there, and when you rotate it by another 90 degree, again that height gets reduced. So, ultimately what happens, the cross sectional area it may maintain the same cross sectional area, shape, but the dimension will keep on changing, and with the result that its length will keep on increasing. So, here h naught will get reduced, w naught will get reduced, but length, of course, length is not shown here, that will get increased. So, that is what will happen. So, in this case the material deforms under compression, and simultaneously with the there is a considerable spreading in the lateral direction. So, that is what its cross sectional area gets reduced, and when you are considering the constant volume relationship, we can find out how much length increase is there. The simplest open die forging is the cogging, a billet between flat tools to reduce the cross sectional area, and in this when you talk about the open die forging, the term which comes is coefficient of spread. Coefficient of spread defined by S is equal to the width elongation, the strain in the width direction, divided by strain, that is positive along the thickness direction. Sorry, the strain along the width divided by strain along the thickness. So, that is S is equal to the ratio of log W 1 by W 0, and along the thickness it is just compressed. So, log H naught by H 1. This is that in open die forging the spreading means. Because of the barreling of the bar due to cogging, it is difficult to measure the width natural strain, but you can easily measure the increase in the length, because using the constancy of volume relationship, that is nothing but H 0, W 0, L 0. So, volume constancy, volume constant is equal to H 1, W 1, L 1. So, in this case, from that we can find out that relationship if you just take the natural logarithm log H 1 by H 0 plus log W 1 by W 0 plus log L 1 by L naught is equal to 0. So, maybe this was our first relationship, this is your equation number 2, this is your equation number 3 if you do that. So, if you substitute into this equation 3 into 1, so equation 3 into 1, we can get this relationship 1 minus S is equal to length elongation by thickness contraction. That is equal to log L 1 by L naught divided by log H naught by H 1 is. So, this relationship that is equal to 1 minus S. So, in this expression, if S is equal to 1, then we can say the deformation, the all deformation is itself as a spread, as spreading is there. If S is equal to 0, the elongation is taking place. Okay. So, then the deformation goes into elongation. Now, you will find that this the spreading depends chiefly on the bite ratio. So, bite ratio, that means S is equal to the bite ratio is given by B by W naught. B is the top punch where it is in contact with that, it is compressed between that width of that part, okay, that distance at which it is contacting. So, from that part only it will elongate. So, that is why it is called as B by W. So, S depends chiefly upon the bite ratio. From experimental this one, the people found that as B by W divided by 1 minus B by W by this relationship, the bite ratio depends. Now, our this equation number 1 also can be expressed in the terms of spread law. So, the spreading law that is beta is equal to 1 by gamma the whole raised to S, where S is the spread, where S is equal to spread and beta is the spread ratio, which is defined by W 1 by W naught, because spreading is spreading in the radial direction, okay, and the gamma is the skews ratio, which is nothing but how much it is compressed, H 1 by H naught. So, this ratio. But this cogging, when you tell it, so open die forging has certain drawbacks. One is that since only a part of the surface under the bite is being deformed at any time. See, I mentioned earlier also, only a small area of the total length of the piece is being compressed. Okay. The remaining length is not pressed at a simultaneously. Okay. Then there is a danger of causing surface lapse, because if I just press between this and between this, these are the top punch, top die, and this is the bottom die, and this is the ingot. After deformation, you will find that it is like this. At any point, I am just telling. Okay, it is like this, or maybe like we can say that this part was elongated also. Okay, so now the next punch will be somewhere here. Next compression will be this area. So there is a here, if the deformation is very large, this will come and metal will flow, and then what you will end up is that there is a lap. So metal will come over that. So there is an overlapping in that. That is why it is called as a surface lap. So there is a chance of formation of surface lap in this case if the deformation is very large, especially. Okay. So at the unforged portion of the workpiece, you will find that. So it is like if it is too large, it will be like shearing, and there will be a step which is formed. So next one, when it comes, metal will just flow here, and then you will have a lap at this region. Okay. So that is not, that is undesirable. So you should know that is one thing. So and how we can do that? These laps will form if the deformation is above certain critical deformation, critical strain. So below that it may not happen, but above that it is going to happen, because the sideways barreling also is going to take place in this case, and that will always cause for this one. So if your deformation, if your strain is very large, the chance of lap formation will be there. And for avoiding the lap, okay, to avoid laps, the skews ratio may be kept below 1.3. So that is one. Now second thing is, this open die forging is done for is being carried out for reducing the cross sectional area of large pieces. So in that case, your deformation has to, the deformation has to reach the center of the piece. That is also necessary. Otherwise, what will happen? Only deformation will take place at the surface, but at the center nothing will happen. So to ensure that each billet is deformed through the center, the bite ratio should be less than 1/3. So in open die forging, you are going to deform the large billet. So when you are wanted to do that, the main purpose of this is mainly to break the structure, especially dendritic structure, coring, segregation, all those things you have to change. So the deformation strain should penetrate up to the center. So if the strain is less than certain amount, the whole purpose will not be met. So for that case, bite ratio for the deformation to ensure that billet is deformed through to the center, the bite ratio is it should be less than 1/3. So this ensures homogeneous deformation. Minimum inhomogeneous deformation. Now, if you look at that in open die forging, the load required to forge a flat section in open dies. So, the load for forging a flat section in open die forging P is equal to sigma bar A C, where sigma bar is the average flow stress and C is a constant, A is the area, sigma bar is the average flow stress. A is the cross sectional area of the billet and C is a constant, is a constraint factor we can say, which is constant, and with a constraint factor to allow for, to accommodate, allow for non-homogeneous deformation. You know that earlier now about the deformation zone we have decided that the deformation resistance increases with the delta. The deformation resistance increases with the delta, which is nothing but h by L, we have discussed earlier. So, there are cases where from the strip line field we can find out that one relationship is equal to 0.8 into 0.2 h b by b. So, that we can say 0.8 plus 0.2 delta. So, this is from strip line field theory. People have arrived at this relationship. Okay. So, now we will come to closed die forging. So, in closed die forging, it is not that as simple as we have discussed. The deformation in a closed die forging is very complex, because the metal has to flow during the deformation compression, it has to flow in the lateral direction and it has to fill up the intricate parts of the material, and during the metal flow there will be friction, there may be a lap which can form. So, that should not be there. The die should be completely filled and any excess metal has to squeeze out through the flash, land and gutter. Okay. These things are there. The component shape is a very deciding factor for this purpose in closed die forging. And closed die forging you cannot get the final, because this is a component itself you are going to get it, which are to be put into use. And normally you will find that automobile industry, the crankshaft, connecting rod, many of these things are made by forging. The hook of a crane, this is all made by forging. So, in all these things when you look at it, it is not a one step process, and which we have discussed in our first lecture. So, it consists of several steps, okay? And the intermediate steps is necessary for finding out the especially when the component is very complex, okay? And you are designed for that each intermediate steps, it requires a considerable experience and skill. So, this is very important. Now, overall success of the forging operation, it requires an understanding of the flow stress of the material, an understanding of the frictional conditions between the die and the billet at that operating condition, and an understanding about the flow of material in order to obtain an optimum geometry for the dies. So, it is not that anywhere it will flow, you have to know in which way it is forming, so that other defects are not formed, like laps, cold shut, these things should not form. So, you should have an idea about the flow of the material inside the die when you are operating. So, if you look at the rationalizing the design of closed die forging is basically by the classification of shapes which are commonly produced by this thing. So, a large amount of work has been carried out in terms of forging, closed die forging, and depending upon the complexity of the shape, you get it can be classified whether it is very simple or it is complex or it is very difficult and other things. So, like you can see that it is divided into class 1, class 2, class 3, like that it is there, where the class 1 is the compact shape generally which is spherical or cubical. So, that means if it is cubical, it is L is equal to B is equal to H norm or approximately equal to that. The shape can be classified as very simple case, that is a class 1, or if it can be a spherical case also. It can be a cylindrical case also, cylindrical samples also, where H is equal to your D, the height of the cylinder is equal to diameter, or maybe approximately equal to, not very long. Okay. So, in that itself, class 1 itself, you have different groups, say 101, 102, 103, 104. So, in this 101, there is no subsidiary element, it is a simple sphere, it is a single cylinder, or it is a single cube. So, in that case, you call it as a subgroup 101. So, class 1 subgroup is 1, that is 101, you classify it. And now, when you move towards the right, the complexity increases. In this second case, maybe a unilateral subsidiary element is there. On this spherical part, you have a cylindrical part here as an attachment. Okay? A subsidiary element is there. So, then its complexity slightly increases. So, or maybe in the cylindrical piece, you have a rectangular piece as a subsidiary element which is there. So, this complicates the forging die. Now, if there is a cube, you have a small cylindrical piece as a subsidiary appendix type thing which is there. So, there also it complicates the shape, but it is not very, very complicated. So, that is why in the subgroup also, this is the most simplest case, this is the most simplest case, then comes this one slightly complex, but in this case, no, when you look at it, it's a rotational symmetry element. For example, in the sphere, on if you have along the seam type thing, you have a like a Saturn ring type thing. No? If you have something like that projecting across the periphery or diameter and other thing, then it becomes much more complex. Or single cylindrical piece is easy to make, but in that if by forging, but in that if you wanted a hollow cylindrical piece, it becomes difficult because that you have to provide facilities for that hollow part. So, in the die, both the dies it is required. So, then it becomes a very complex thing. Similarly, for a cube also at the on the center of a face or on one part of the face, you have some part throughout the projection if it is there, then it becomes much more complicated because metal flow conditions will be complex. So, that is what. And finally, the last subgroup will come under unilateral subsidiary elements, more are there. Okay. So, you have say both this rotational subsidiary element as well as this subsidiary elements are there. So, maybe multiple numbers are there, here there is one, here there is an extra. So, here these two cases are there, and in this also you have all sorts of. So, this type a piece to forge in and get it into this case it is very complex. So, when you move from the left to the right, the complexity increases. Now, from class 1 when you move up to class 2, class 3 or along this figure, if you come down, you will see again the complexity increases. So, here it was spherical case or cubical case, or but when you come to this you have a disc shape. So, the diameter is much larger than the thickness, or if it is a rectangular piece also, then you have the disc shape. It can be circular or square. The parts are circular, square and similar contours, cross section piece with the short arms, upset heads and long shapes, flanges, valves, all those things are coming. So, for example, in a single shape, in the simplest case 211, this classification 211, it is a very simple disc with a unilateral, with no unilateral element. So, when you come to this one, there is no subsidiary elements, 211, there is no subsidiary element, simple disc. But when you come to see, if there is a disc with a hub, maybe this may be used for some flywheel or something if you wanted, then there is a disc and there is a hub, there is a complexity coming into picture compared to this part. So, here compared to this, here it is slightly complex, because in one of the part you have to provide provision for this projection. Similarly, when it comes to say a hollow part inside that, so you have a hub and a hub which is hollow, the complexity is going to be much higher. So, similarly here there is a disc, but with a rim at the surface, only at the end there is a rim part is there, then that also is difficult to forge. It is possible, but it is difficult compared to the other cases. And similarly, now with the rim and hub both coming, it will be much more complex to get, because you have to have different more and more operations with each changing in this case operation, and finally, you have to provide for the facility in the finishing operation also, or maybe blocker die also you have to provide it. So, one is intermediate process is coming into picture, then your die has to be should be able to accommodate not only in the finishing die, but also in the blocker die this has to be there. So, blocker die also has to be designed accordingly. Similarly, when you come to this 22, the disc shape with the bilateral elements, here it is unilateral element, but with the bilateral elements. So, maybe a hub is there on both sides, that is again complex, and hub and a hole and rim which is there on both the sides. So, here, so there this complexity still increases. So, this classification when you come, so here examples are flanges and valves. Now, the class 3, you will see that roughly 70% of the forgings fall under this class 3, which is much more complex compared to shape class 2 and shape class 3, class 1. These are oblong shapes. You will see that one length is much higher than the other. So, you can see that length higher than width, much higher than the thickness, and then there is going to be slightly complex compared to other one. Example is the principal shape element with a straight axis like this. You have this a rod where the length is much higher than the diameter without any subsidiary element, or a rectangular block, plate or whatever it be. So, that is also the simplest among this case, but in that if there is a subsidiary element here, then it becomes difficult, complexity is there. Similarly, you have this case also, normal to the longitudinal axis, the die also has to be designed, the blocker die has to be designed, and you have to have an extra process by which the metal should be gathered before it reaches the blocker die. So, the intermediate operations are going to come, whereas in this first category no subsidiary elements are there, it is quite simple. Okay. Now, with open or closed fork element is coming. So, that is it increases, the complexity is still higher. So, when you move this side, it becomes more and more complex. Now, there are forked elements are there, okay, or this type of shape is there where a hole is there and other things. So, then it becomes much more complex. Now, with the subsidiary element which are asymmetrical, not symmetrical, then you may encounter other difficulties like die shift and other things may come into picture. So, you may have to provide some extra facilities so that the die shift is not taking place, and it becomes the die itself becomes difficult, the intermediate stages increases, and you see that with the 2 or more subsidiary elements of similar shapes, that is much more complex. So, when you move to a second longitudinal axis of principal shape element curved in one plane, so here it is there, curve is there, here it is there, curve, here it is curve, you need intermediate process for closed die forging of this. Similarly, the case is here also. So, here also you can see, so I am not going to discuss much about this forked shapes and other things are coming. So, here too much complication is there. And finally, the last part, the longitudinal axis of principal shape element curved in several planes, see like this. This type is extremely difficult, a large number of operations before the blocker die is will have to be done. You have to bend it one way, you have to bend it the other way, all those things are coming. Here if it is there, say here the cross sectional area is different, all those things. So, your operations keeps on increasing with the complexity of the shape. So, shape classification of forgings has been carried out, and it is based on that you find out what are the difficulties and other things. So, you can say this is taken from published paper only. So, that is it. And about the when you are doing the forging, how the flash is formed, gutter is formed, that part we have discussed. Okay. So, with this this class is this lecture is over.